So the title of my talk is Fabrication of Biodegradable Particles with Tunable Morphologies by the Addition of Resveratrol to Oil and Water Emulsions. So to begin with, I'd like to discuss some background into the formation of biodegradable polymer particles and their uses in drug delivery. So this is actually a fairly developed technique, and it involves an oil and water emulsion, which involves solvent, polymer, and drug dissolved in an organic phase, and an emulsifier and surfactant, which are dissolved in water. And these two are mixed together at high speed, and this forms an emulsion. And an emulsion is just a stabilized system of organic and water, which are immiscible, stabilized by this surfactant into microdroplets, which you can see here. And then in step two, this emulsion is added to a larger volume of water. And this leads to an extraction, which is shown in this figure here. What happens is that the organic solvent is extracted out of the microdroplets into the water phase due to its slight solubility in water. And this will cause that droplet to shrink. And as it shrinks, the polymer and drug, which are not soluble in water, will harden, precipitate into solid form and form particles, as you can see here in this nice SEM image. So this is some of our particles. So they're nice uniform size and very smooth and spherical. So some of the applications of the systems, this has been widely used, as I mentioned. Polymers used are polylactide coglycolide, shown here, which is a copolymer of lactic acid, glycolic acid, polycaprolactone, polylactide. One of the most commonly used emulsifiers is PVA, polyvinyl alcohol, shown here. And some solvents that are used are dichloromethane and ethyl acetate. Dichloromethane being far and away most common. It's also volatile in addition to being immiscible in water, and this helps that extraction step. Ethyl acetate has recently been used due to it being less toxic if it ends up being found in trace amounts in these particles. So here's some examples of FDA-approved PLG microparticles, not an extensive list, but just a couple. Vivitrol, Lupron Depot, and Resveratrol. So in our lab, we wanted to take this idea of PLG particles and see if we could improve the delivery of resveratrol. So resveratrol is this molecule shown here that is produced by several plants, grapes, and it's found in red wine. It's been shown to protect mammals from high-fat diet, enhances insulin sensitivity, it's anti-inflammatory, but it suffers from low bioavailability in humans. Any sort of clinical trials or mouse models with this has found that it doesn't have great effects in vivo simply because it's hard to get it to the tissue of interest. So our idea is that we would encapsulate it in a particle, deliver it to the tissue of interest, and it would release its payload in a controlled manner. So that's exactly what we did. We loaded PLG particles with resveratrol. And so in that system that I described earlier, you need the drug to be soluble in your organic phase, but resveratrol was not soluble in DCM. It was, however, soluble in ethanol, which we used as a co-solvent and used that as our organic phase. We dissolved, mixed it in PVA and water, produced our PLG particles. What we found was that we didn't produce these smooth spherical particles that we would normally. Instead, they were really crumpled and had this strange, almost raisin-like morphology. And so this was really puzzling and interesting to us because the whole idea of an emulsion, why it forms smooth spheres, is that that emulsion is trying to reduce the interfacial tension between the organic and the aqueous phases, and the sphere is the geometry that will reduce interfacial tension. So whenever you produce something that doesn't have a sphere, it's actually not favored, and so there must be something going on here. So our question was, what is the mechanism for this? And we wanted to pursue this because this could potentially be useful to be able to produce or control morphology in drug delivery. And also, can we control this to a point where we could produce spherical particles for resveratrol delivery? So to begin with, we took our emulsion system that we're using to make resveratrol particles, and we looked at some videos just looked at them under the light microscope and see what was happening. So we would predict that those oil droplets, as they were losing their organic solvent, would shrink. And in a normal system, they'll shrink uniformly. So what we see in this first video is that, yep, they shrink very slowly. The organic was releasing and they stay spherical. When we look at the resveratrol one, they shrink much more rapidly and they immediately crumple, almost as though a beach ball was deflating, which we thought was an apt analogy for this, and which I'll get into a little bit later. So looking at a time lapse of these videos, which is what this slide is showing, we did 3 conditions under the microscope, just blank DCM, the DCM plus that co-solvent ethanol, DCM, ethanol, and resveratrol. And so the reason we just did ethanol here was to make sure that ethanol wasn't one of the reasons that this formation was happening, this strange morphology, and indeed it wasn't. Both the blank DCM and blank DCM plus ethanol had smooth morphology. When we added resveratrol to this group, that's when we started to see these strange, almost spikes coming out of the sides of these particles. So a question that came, or a possibility that came to mind was that we could be, resveratrol is this crystalline solid, and we could simply just have crystallization. And that could be causing these crystalline-like edges on the surface of the particle. So we looked at XRD, which is X-ray diffraction, which is a technique looking at the crystalline structure of solids. Crystalline structure being denoted by sharp peaks. So this bottom black graph shows resveratrol, shows many sharp peaks in the diffractogram. The second one, which is orange, is the blank PLG, is an amorphous polymer. So you see there are no sharp peaks because there's no alignment of those molecules. And then the top one is when we took the polymer and resveratrol and we just mixed it together in a physical mixture, just solid mixture. And we see those peaks again, in addition to the amorphous structure of PLG. When we make the polymer or the particle in the emulsion, something different happens. We don't have those sharp peaks. There does remain some peaks here. So there still are some crystalline domains, but it's not nearly to the extent that we would have expected all of that resveratrol that we added to be simply crystallizing on the surface. So we suspected there was more to the story here. So we looked at next the amount of co-solvent added, and so and we hadn't quite pieced apart what was going on with the ethanol in this system. And so in the first frame here, looking at A and D, we had 25% by volume ethanol with 4 mg per mil resveratrol. And importantly, in the first experiment, we had 10 mg per mil resveratrol. We still formed some irregular structures shown with these red arrows, but there were far fewer. We went next to that 25% ethanol with no resveratrol, which I've already shown was smooth in panel B and E here. And then we looked at, this was interesting, 10% ethanol, 4 mg per mil resveratrol. And so when we did it this way, we had smooth particles. So simply by changing the amount of ethanol from panel C to panel A, changed the morphology. So definitely there was an effect of the co-solvent. The co-solvent was necessary for this effect. So the next thing we looked at, so we kind of established that ethanol portion. Now we wanted to know, with regards to resveratrol, what potential uniqueness of resveratrol is there that causes this morphology change? So looking at the molecule, which is in panel C here, we see that there are OHs on either side of this trans-Thilby molecule. And we wanted to deduce how important were these OHs. So looking at 4 resveratrol-like compounds, trans-Thilbene, pinosylvane, picoadenol. On the left, trans-Thilbene has no OHs, forms smooth particles. Pinosylvane, which has 2 OHs, also forms smooth particles. And then picoadenol, which has 4 OHs, hardly formed particles at all that we could discern. And in addition, I put the mass yields here. The mass yield decreased significantly for this one. And this was suggesting that the emulsion almost wasn't stable. It wasn't forming particles. We got just kind of this goop that came out. So what was going on here? We've done encapsulation with hydrophobic molecules before, which is what this system is designed for. And you don't see these morphology changes. Either you get high or low loading, but they always stay smooth. So there seemed to be something interesting going on with resveratrol in particular. And what we noticed was that the log P, which is an indicator of hydrophobicity, seemed to track that as we decreased the log P, in other words, became more hydrophilic, we were reaching this point right around 3 or 2.9, where these molecules, which are not soluble in DCM and only soluble in ethanol, cause this strange morphology. And so this, however, what we really learned here is that resveratrol is right at that sweet spot, 3.1, that allows us to tune the morphologies, retain particles with a decent mass yield, and they had this very interesting morphology. So we also knew that co-solvents were important. So we looked at different co-solvents, and we found that they caused different morphologies, which is shown here. Panel A shows DCM and ethanol, B, DCM and methanol, and then panel C is DCM and acetone. Ethanol and methanol had very similar morphologies, but acetone was distinctly different, and it had more sharp, triangular, almost geometric-like shapes that didn't appear as cloudy under light microscopy. In addition, they were more transparent, like blank particles would be. And these shapes kind of led us to an interesting hypothesis, which was that these particles, resveratrol is causing a shell to form at the surface, and this shell is then decreasing, or is, deflating in essence. And the reason we say that is simply because of the shapes shown here. That acetone shape appears like a basketball as it's deflating, whereas the ethanol and methanol shapes appear like paper crumpling almost. So the final piece of this puzzle that we kind of looked at was that using a different solvent causes a spherical morphology. And so DCM and ethanol clearly were causing irregular morphology. But could we find an immiscible organic solvent that also dissolves resveratrol? And that was ethyl acetate. And when we did the fabrication, they came up smooth. And there was no sign of this irregular morphology. This really led us to conclude that co-solvent is necessary, and that the co-solvent is aiding this formation. All this information that we gathered so far led us to this sort of mechanism, which is that resveratrol and DCM and PLG are in the oil phase. Ethanol, which is soluble in water, is leaving first. Resveratrol, being only soluble in ethanol, is getting caught at the surface. And this is leading to this surface almost hardening very early on in the extraction step. And as it hardens, the shell then crumples in on itself as more DCM leaves. And this is borne out by the fact that we got those different shapes with methanol, ethanol, and acetone. Looking at the solubilities of those solvents in water, acetone has lower solubility and would leave that system slower than, say, methanol and ethanol. And you would expect, if it were forming a shell at the surface, that it would have these sharper indents, which is exactly what we saw in the acetone system. So our conclusions here are that resveratrol with co-solvents cause morphology change in polyester particles. Morphology change is dependent on a combination of co-solvent and resveratrol, which is shown because when we dissolve it in ethyl acetate, we didn't get the morphology. And we actually have the ability to tune the amount of resveratrol, the morphology, by the amount of resveratrol added and also the co-solvent used. So we can make very irregular particles all the way to picoadenol, crazy particles, sharp particles, and then lesser amounts of crumpled morphologies, depending on the amount of resveratrol we add. And then using this method to tune particles could be useful in biological systems that are sensitive to morphology changes. A realm in particular is in immune cells have been shown to be very sensitive